Let's see. Today is Tuesday, July 26th. And I want to go over like the schedule for the next 2 weeks because the class is almost over as it happens. Feels like the summer rushed by real quick. Today is the 26th, and today is the day that Test 2 is opening on WebAssign. That means that starting today and running through Saturday night, you can take it. You can take it at any point between now and then. So you don't have to do it today necessarily. Just like last time. So it's available as of now. You can, once you open it at any point in the next 5 days, you can work on it at your own pace. It'll start a 5-hour timer to complete a 1-hour test. There's 10 questions about the electricity magnetism content from the last month. And when you take it, you can send me any questions you have. And then when you're done, you send me your work, as with last time, and I will give you partial credit based on your work. That is running through to this Saturday, and you can take it whenever is good and convenient for you. Other articles, other scheduling things to be aware of. This is the last normal week of class meetings, last full week at least. Tomorrow, my plan is for us, at any point this week, you can come in with study or test-related questions. That's fine. Do that literally any time. But to step through other miscellaneous things from the rest of the week, tomorrow and Friday, in addition to review questions, I will be spending extra time, any time in these lecture calls that isn't spent on review questions. I'm going to be talking about waves and optics, and an additional chapter that will be on the exam but isn't on test 2. So if the way you process information makes it such that it's not optimal for you to be hearing content that won't be on test 2 as you're studying for test 2, I'll be recording it and you can catch it later if you need to. But that is what I'll be talking about in these class calls this week is waves and optics, because it is part of the syllabus and it is good stuff to know as just a part of how physics works. So, and I'm depending on how much questions you guys have today, I'll probably even start talking about that today. It's not a lot of material. I'm not planning on going into like big math details about it. I just want to cover the basics of. I want to cover the things about light that are important to know and how it affects the human society as it currently exists. So, scattered throughout this week will be discussions about that. Main things about this week are definitely the test, which is live now and will run through Saturday. And we do have our last in-person lab this Thursday. We will do 2 labs on that day. One will be a resistor circuits lab, and the other will be a electromagnet. I forgot English for a second there. Electromagnet motors lab, where we'll actually be building a small sample motor to see how those work. That'll be the last in-person assignment. And in addition, because we need to get 10 labs in during the term, I'm going to be posting 2 very short additional assignments, additional like out-of-class lab assignments. There won't be any waves homework necessarily, but these 2 out-of-class labs will kind of be like the last homework assignment. They'll count as labs, and you can. I'm going to make sure that they are posted and emailed to you today, just so that you have them and you can start them whenever you want. But those 2 very short extra lab assignments that you can do on your own time. Those will be labs 9 and 10, and that'll round out our number of labs this semester to 10. I feel like I'm rambling a little bit. So, important things for this week. 1, test is launched. Take it at any time between now and Saturday night. 2, in-person lab on Thursday. 3, the last 2 remote assignment independent labs will be given out soon that you can do on your own time at any point between now and the end of the semester. Those are the main things to be concerned about for this week. And at any point this week where we're meeting and no one has any needs or questions, I'll just be going over some additional information about waves, namely optics. Now, next week is actually the last week of the class. Next Monday is August 1st, and summer finals for the final term of the summer session is next Thursday-ish, approximately. So, we'll take test 2 this week. We'll spend next Monday, or sooner, if everyone wraps up before then, going over, as soon as everyone's done with the tests, I'll make sure everyone has their score, comments about how they did. We can look over and we can talk about it together. And then next week, we will spend time specifically going over exam stuff. So next week, Monday, Tuesday, and Wednesday, that's all, as far as I'm concerned, reading days, exam study time. And so we'll have... I forgot how to talk. Sorry. During next week's meetings, we'll have at least one day that's just me going over all the information that will be on the exam, making sure everyone understands what will be on it, how it will work. Other days will be study days. Come in as you have questions. And then the exam will launch next Thursday. You'll need to take it. You'll have 6 hours to take it at any point between next Thursday and next Friday. And actually, let me check the academic calendar real fast. All right, yeah. So the exam will open middle of next week. You'll have same as the test. You'll have a 6-hour window for over the next couple of days after it launches to take it. It'll work exactly like the test. It's just basically 2 tests crammed into one. There'll be study material for it. I give a new list of practice questions for every test or exam. So once you're done with test 2, if you want more questions to be able to study for the exam specifically, there is already some study questions on WebAssign, and we can look over them together, along with study guides, formula sheets, lists of things to be familiar with, etc. That's going to be what we're dedicated to next week. And the exam is specifically going to be over the latter half of next week. I think I'll put it up on Wednesday, and then it'll run through Friday, because I'll need to get the grades done and in and submitted by the Monday after that weekend. So that's basically the itinerary for the rest of the course. Test 2 and wrapping things up this week. Next week is exam prep, followed by the exam itself. Any comments, concerns, needs, opinions about any of this information, please let me know. Okay. Again, if you need anything at any time, if the test isn't working for you, or if you run into an issue while working on it, or if any of these scheduling details that I've mentioned today don't end up working with your schedule, something changes, if you need to talk to me about it, please do. I know I make that point a lot, but it's very important. What was my next point? Okay. So, top priority this week is absolutely test questions, test studying. So, whatever I'm currently talking about, because again, I want to talk about some extra stuff about waves and light, but test questions, test 2 stuff always takes priority over that. So, interrupt me. please, if I'm doing the wave stuff and you have a question about electricity, magnetism, anything from test 2, or even about the exam. So again, if you guys don't need anything right this second, if there's no questions right this second, then my plan is to at least begin talking about some of the details for some of the notes for light and waves and stuff. Again, I'm going to be filming it so that you can come back and watch it again later if you'd rather get test 2 out of the way first before technically absorbing new material. It is related material because, as it turns out, light is secretly both an electric phenomenon and a magnetic phenomenon. So it is actually related to what we've been talking about. Light is a very odd thing, and I do enjoy talking about it, even though it is still very mysterious in a lot of ways. I'm rambling again. So, any questions, please ask them now. If there's no questions, I'm going to begin talking about light and waves for a little bit. All right. So, just make sure everyone's clear. This is information that will be on the exam, but will not be on test 2. Just want to make sure that's absolutely clear as you're studying. So, waves. We're going to focus primarily on light because, well, it depends on how long ago your Physics 1500 class was and how much material that your section got through in that particular semester. You've probably talked a bit about sound waves and other mechanical waves at PC so far. So we're going to mostly focus on light because, like I said, it's related to the electromagnetic phenomena that we've been talking about this past month. But a lot of the things that apply to light also apply to other types of waves like sound, because all types of waves are fundamentally similar in a lot of ways. And it's important to talk about the different types of waves because at least 2 human senses are based on how they work. The function of your eye and ear depends a lot on the mechanics of waves in general. But it shows up in a lot of other places too. South Carolina's been having a lot of earthquakes recently, and technically earthquakes are seismic waves, and you can detect other types of waves just by feeling them with your body. So, useful information, and that's why we're talking about it. I'm going to be skipping around the notes a little bit here. That is a very hard to read font color. Okay. So, as a brief refresher, and I'm hoping this information is familiar to you, waves are essentially traveling energy. If you think about waves, and at least in the English language, when you say the word wave, the thing most people tend to first think of is like an ocean wave. And every type of wave, including ocean waves, is basically traveling energy. Energy moving from one point to another. In the case of an ocean wave, energy from the wind and the tides further out travels through the water to get to the coastline. And for all types of waves, an important thing to note is that only the energy itself is actually traveling. if you examine ocean waves very closely, the energy for the ocean wave starts way out at sea. You might not see a wave forming until it gets close to the shore. Like, you might not see the shape of the wave forming until it gets close to the shore. But the energy for the wave starts way out there. And that energy begins moving towards the coastline. And as the energy gets closer to the coastline, you can kind of see the wave shape taking form. And then the energy will crash into the shore and knock over anything that's in its way. Note that the energy is using the water as a medium to get from out in the ocean to the shoreline. The water doesn't necessarily travel along with the wave. Again, the energy for the wave starts way out at sea, and the wave doesn't grab hold of every water molecule that it touches and drag all of that water with it to the coastline. Because if it did, if it brought all of the water that the wave had ever interacted with to the coast, you'd have tidal waves literally every single wave. The energy is what travels. The water does move. The water moves as the energy travels through it, because when matter has energy, it tends to do stuff like move around. But the individual water molecules that the wave happens to occupy as it travels don't all come with it. Rather than say the water out here comes with the wave to shore, it's more accurate to say that as the wave energy travels through the water, the particular water molecules at any given spot the wave travels through move as the wave passes through it, but once the wave passes through it, those water molecules go back to normal, because it's only traveling energy. This is true of every type of wave. As an additional example, sound waves, rather than using water to bring energy from place to place, use air to bring energy from place to place. Whenever you speak, you are putting energy into the air. That creates literally a ripple, a wave in the air. That's energy moving from your vocal cords towards someone's ears. And the energy is the only thing that really travels from my vocal cords to someone's ears, because, again, sound waves use air to travel through. The sound doesn't take all of the air that it moves through with it. The energy just passes through the air and then leaves the air alone once it's done passing through it. The sound doesn't bring all that air with it, because if it did, you'd create gusts of wind every single time you talked. All of the air that the sound travels through does not go with the energy. The energy just moves through it. Same is true for earthquakes. The energy released when two fault lines move past one another travels through the ground, but it doesn't bring all of those rocks with it. If it did, every single earthquake would destroy the continent. So, for all types of waves, energy is the only thing that travels. All the waves that I've just used as examples are called mechanical waves, because it's energy traveling through some physical object. Ocean waves travel through water, sound waves travel through air, earthquakes travel through the ground. Solid, liquid, and gas. These are called mechanical waves because they require a mechanical medium in order to work. Sound waves need air in order to propagate. This is why you can't hear anything in space. There's no air for sound to travel through. So all mechanical waves require some medium. But light is not a mechanical wave. It is still a wave, so therefore it is traveling energy. But light is not a mechanical wave, because light does not require a physical medium in order for that light wave to travel through something. Light can travel through physical medium. For example, every single photon of light that you have ever seen in your entire life has been traveling through either air or water, possibly through glass, but eventually it hits air again before it hits your eyeball. You've ever only observed air as it you've only ever observed light as it traveled through some medium because you've been surrounded in air your whole life. But light can travel without a medium because it can travel through the vacuum of space. There's no air in space, that's why sound doesn't work there, but light can still travel through space. We know this because astronauts can still see things up there, and because we get light directly shining on us from the sun, which is a very long distance away through that vacuum. So light is a different type of wave. It is still traveling energy. That's still the case. That's true of all waves. But light is an electromagnetic wave. Mechanical waves require a physical medium. Electromagnetic waves do not. So that means that light is physically made of something different to these other types of waves. And they both still exhibit wave-like behaviors. Everything you've talked about, everything you've learned about waves before is still true. For example, these are some vocab words related to waves that you've probably heard before. A wave's amplitude is the physical size of the wave. Wavelength is the physical length of the wave. Frequency, it tells you how many full waveforms pass every single second. You probably talked about frequency in relationship to, what pitch of sound you're hearing or what color of light that you're seeing. As a wave, light still has all of these vocab words. But unlike sound, which is, again, mechanical and requires a medium, light and other electromagnetic waves are physically made of something slightly different that lets them travel without a medium. And what light is physically made out of, we call it an electromagnetic wave because it's literally made out of electricity and magnetism. Over the past week or so, as we've expanded from talking about just electric fields to including magnetic fields in our discussions, I'm hoping that it's become clear that electric fields and magnetic fields are related. They're different things, but they are still related. They're opposite sides of the same coin. And despite being different things, they do still interfere with one another. Electric fields do interfere with magnetic fields in a way that they neither themselves would interfere with, say, a gravitational field. Gravity is a different phenomenon, whereas electricity and magnetism are linked in such a way that their fields do affect one another. We've demonstrated this when we looked at how a magnetic field affects a charged particle moving through the magnetic field, how moving charges in a wire can generate their own magnetic field. The two phenomena are fundamentally linked, and they do interfere with each other, specifically at right angles. If you'll remember the right-hand rules stuff from last week, the force that an E field and a B field exert on one another always depends on a right angle relationship. If you'll remember, if a charged particle is moving, say, in this direction, and a magnetic field points in this direction, the force between the two will point in this way. All three of those vectors are at right angles from one another. So, in general, B fields and E fields have an odd right angle perpendicular relationship with one another. This is sort of epitomized in what we currently believe the physical structure of light to be. If you've heard the term electromagnetic wave before, and before today, I would assume you at least heard it before. I would hope that you've at least heard the term before. Light is called an electromagnetic wave because it is physically made of both an electric field and a magnetic field oscillating in tandem together and traveling together in the same direction. Now, this is obviously something that you wouldn't have witnessed on your own just naturally in life, because even though we humans are able to see light, the human eye, when functioning optimally, is capable of detecting light. You are not able to really see an individual photon of light. Photon is the term for a specific packet of light, a specific instance of light. The sun is constantly creating tons of photons. Photons are the smallest unit of light that exists. A single photon could be considered to be a single electromagnetic wave. Again, photon, if you haven't talked about photons academically, it's a term that comes up often enough in scientific discussion and just media that people have at least heard the word before. But the term photon refers to the smallest instance of a single beam of light, if it helps to think about it like that. Human eyes can detect photons, but you can't really identify individual ones. You can't really, look out into the universe and see specifically the motion of a single photon and observe the two fields that it's made out of moving in tandem. So this explanation is kind of hand-wavy. It's something that you wouldn't have witnessed before. But science's current understanding of what light is demonstrated here in this picture. We have an oscillating electric field oscillating up and down in the y-axis here. So it is a wave of electricity, if you think about it. This shows a waveform of an electric field oscillating up and down as it moves through space. So you can envision this as the photon being fired this way, and the E field is oscillating up and down as it travels, kind of like how a normal ocean wave travels this way, even though the waveform looks like it's shaking up and down. The energy goes to the right, but the waveform oscillates up and down as it travels to the right. Light is physically made of an electric field oscillating, you could say vertically, as it moves to the right. But in addition to that electric field is also a magnetic field that is oscillating perpendicularly to the electric field. So if the electric field is oscillating up and down, the magnetic field will oscillate in and out, back and forth in the x-plane instead. The two fields exist and oscillate perpendicularly to each other, but they still move together as one in the same direction. They're both traveling in the same direction. They're just oscillating, shaking in different axes. I'm hoping that the picture and my hand waving can demonstrate this. Again, light is weird, to the point where we still don't understand a lot about it. This is the best representation of what light physically is that we currently have. But because we can't really see or interact with single photons to actually grab one and study it and see what it's made out of, some of it is still guesswork. So I'm giving you the best information that currently exists in the way that we currently understand it. But this is why it's called an electromagnetic wave, because it's literally made out of electricity and magnetism traveling together at once. A few things that this should say to you is, one, light has no solid nature to it. It's literally energy traveling from point A to point B. If you if you fire a laser at something, that laser is literally just moving energy. There's no matter involved in it. Light isn't made of matter. It doesn't require matter to exist. This is literally a form of energy that can move from point to point and be fired in the form of a photon laser beam. It doesn't need matter to exist, and it's not made out of matter. It is literally traveling energy in the form of these two oscillating E and B fields. And these waves get made when charged and magnetic particles are vibrating in such a way that they emit energy and can create the fields needed to turn that energy into a photon. For example, the sun is made up of a bunch of hot supercharged plasma, so all of the particles that make up the outer layer of the sun are electrically charged at all times. The plasma of the sun has become so hot that all of the atoms have shaken off their electrons, so there's just a bunch of pluses and minuses flying around randomly, separate from each other, too hot to properly settle down and interact. All of those charged particles are energized, and since they're energized, they're vibrating very fast. And when you take an electrically charged or magnetically pulled object and give it energy and it starts vibrating like that, it has the potential to create the E and B fields needed to emit, to build a photon and emit energy in the form of that photon. This is why the sun gives off light, because it's full of super energized, charged particles. And this is why radio antennae can give off other forms of electromagnetic radiation like radio waves, because there's electric current in those radio waves designed to move up and down the length of the object, creating magnetic fields in order to emit information, in order to emit energy in the form of a radio wave. So light is called an electromagnetic wave because it is very much caused by and made out of electricity and magnetism. And the other thing that this should demonstrate, the other point that this hopefully is able to make to you, is that since light is itself an electromagnetic phenomenon, it can in turn be affected by electromagnetic fields. Last chapter, when we were talking about magnetic fields, I mentioned the fact that Earth's magnetic field protects us from the sun. The sun gives out far too much light. The sun gives off more light than Earth needs. We get heat from the sun, we get light from the sun, but the sun is constantly giving out more than the Earth actually requires to stay alive. The magnetic field deflects, Earth's magnetic field, deflects all the excess stuff away. It keeps us safe by just happening to be at just the right strength to literally act as a force field and deflect all the extra light and all the charged particles away that Earth doesn't actually need, such that just the right amount of light gets through and the planet is actually habitable. If we didn't have a magnetic field, there'd be so much more light pouring in constantly onto Earth's surface that the entire planet would just become a sun-scorched wasteland. A lot like how Mercury is. Mercury doesn't have much of a magnetic field to speak of, and that's why it's just the daytime side of Mercury is scorched and uninhabitable. It's basically on fire all the time because there's just too much light coming in. Nothing can exist there because it immediately will melt. Whereas Earth has this magnetic field, and since light is physically made out of electricity and magnetism, a strong enough magnetic field can interfere with its traveling and possibly deflect it. And that's what Earth's magnetic field does, and that's, again, one of the things that contributes to the auroras at the North and South Pole. The magnetic fields are stronger at the North and South Pole since that's where that's basically like the ends of the bar magnet inside of the planet. The magnetic field lines come out or enter the poles, so they tend to be stronger at the poles. Since the field is stronger at the poles, it generates a stronger reaction to the light and charged particles from the sun, and that's why you see the northern lights there, or the southern lights as well. Okay. Light is an electromagnetic phenomenon, which I find kind of cool. Light itself is kind of like the purest form of energy that humans are able to normally observe. Because typically you can only really observe energy when something has it. Energy by itself you usually can't see. You can just tell an object has energy when it's using it to do something. Like when it's moving, or when it's... Actually, that's really the only way that humans are able to detect, is if something is moving. Or if you could also touch it and see what temperature it is. That's another way to check something's energy level. But normally, you can't detect energy by itself. You can just detect that an object has energy. Light is kind of the one exception, because depending on how your eyes work, light can enter your eyes and you can detect that energy. It's basically the purest form of solo energy by itself in the universe, because all other forms of energy have to be possessed by an object. But light, once it's made, once that photon is generated and fired, again, kind of like the sun makes light and then fires it out into space, then it's just going to keep traveling by itself, completely independent of any other object that it could hit or that could possess that energy. It's just going to keep going. It can exist without matter. So, light is, in a way, one of the purest forms of energy that exists, because it's, I think, the only form that can exist by itself. All other forms have to be possessed by something. But once a photon is made, as long as it doesn't hit anything, it can just exist independently as energy on its own. So I find that kind of cool. I've been talking for a second now. Let me know what questions you have as they come up. I'm only going to go a little bit longer today, because again, this is weird new material and I don't want to distract too much from your test studying. I'll just bring up a few more points for today. One thing to keep in mind is that all electromagnetic waves, since they're all made out of electric fields and magnetic fields, they all travel at the same speed. You've probably heard the term speed of light before. Light speed is a number that humans have calculated. Light is the fastest thing in the universe, since its top speed is subject only to how quickly its electric and magnetic fields are able to permeate through free space. So this calculation currently on the left here shows how permeability and permittivity of free space affect the speed of light. The only thing that you would probably need to be familiar with is this number on the right-hand side here. The speed of light, regarded as a universal constant, is 3 times 10 to the 8th meters per second. That's 30 million meters in a single second. Light is the fastest known thing in the universe. Nothing is able to travel faster, and only a few specific other things are able to move at the same speed as it. So that is the top speed. That number right there, 2.99 times 10 to the 8th meters per second, is the speed of light, and that's the top speed out of anything that we currently understand in the entire universe. All light, all electromagnetic radiation moves at that speed. Additionally, since this is a constant, and since physicists talk about it and use it fairly regularly, it has its own symbol. We like to give symbols for all the constants and numbers we use repeatedly in physics. So the variable, the symbol for the speed of light, is a lowercase c. And the reason I bring that up is because you've seen that c before. E equals mc squared. The c in that formula is this. That c is referring to light speed. This is because this formula, E equals mc squared, is part of Einstein's research into relativity, and it's specifically about the energy of an object moving at some fraction, moving at light speed. The energy that something possesses depends on its maximum top speed. That's its own dedicated field of science. You don't have to remember anything about that. I just wanted to point out that that c is something that you've seen before, so if you ever notice or think about E equals mc squared again, that's what the c in the formula represents. The c is light speed, the m is mass, and the E is relativistic energy. Last thing I want to go over today specifically is that light is not the only form of electromagnetic radiation that exists. I'm hoping, in possible previous discussions of waves that you've had in physics or other classes in your past, you've probably encountered the terms frequency and wavelength. These two things sort of describe a wave. They talk about physically how long something is, how long the waveform is, and its frequency, how many waves pass you in a single second. You've probably heard this in relationship to what frequency a sound wave is, or maybe what frequency you've tuned your radio to. I know radios are falling a little bit out of fashion, but FM radio, if you've tuned a radio station set to FM in a car, you're changing the frequency of which that radio is trying. You're changing the frequency that it's tuned to try to receive information. And so different types of electromagnetic radiation all have different frequencies. For sound, frequency determines pitch, but for electromagnetic waves, frequency determines what type of wave it is, and if it's visible light, what color that light is going to be. Light is just part of a family of different forms of electromagnetic radiation based on the frequency and wavelength of the particular electromagnetic photon that was created. We'll talk more about the frequency and wavelength stuff later. For right now, what I want you to keep in mind is that visible light, the stuff that you can see with your eyes, is just one out of several different forms of EM radiation that are all basically the same thing. This list currently on this slide here: radio waves, microwaves, infrared, visible light, UV, X-ray, and gamma ray. Those are all forms of electromagnetic radiation. They are all the same thing as light. They just have different frequencies, and they have different properties as a result of that. They all do different things when they strike something because of their frequency. But they are all basically still the same kind of thing. All of these different forms of radiation, they are all a traveling electric field and magnetic field that was emitted by some object that had energy. They're all the same thing. Visible light is the same basic thing as the radio waves that your phone uses to work and the X-rays that they use in doctors' offices. It's all the same basic type of radiation. It's just different flavors based on what that frequency is. In terms of light, frequency determines color. And we'll talk more about the relationship between speed, wavelength, and frequency and the different forms of electromagnetic radiation later. I feel like I've given you enough to deal with today. We're just going to, for right now, we'll stop just having focused on the electromagnetic nature of light to kind of tie it into what we've been talking about. So, questions, comments, concerns, needs, etc., about any of this information or any of the test or scheduling stuff for the next 2 weeks, please let me know. I'll be hanging around here in this call for the next hour or so. Let me know what you need as you need it. Test is live now. You can take it when you're ready for it. Again, send me your work once you're done. Once everyone's done, we can talk about it together in class. And if I don't see you again today for questions, then I'll see you tomorrow for more questions and probably more talking about light. Let me know what you guys need. See you then.